We will finally learn about this proof technique called mathematical induction. We saw specific situations where mathematical induction is a perfect tool to verify a claim. The situation came up when we determined recurrence relations of execution time functions. This slide shows an example of a recurrence relation. Our goal is to resolve the recurrence relation. To resolve it, we basically make an educated guess, but then we still need to prove that our guess is correct. And that's the point where mathematical induction comes in. What kind of statements can be possibly proven by mathematical induction in general? If at all, mathematical induction is used to prove statements that are made for all natural numbers starting at a given number, say n sub 0. For example, the sum of all numbers from 1 to n is equal to n times n plus 1 over 2 for all natural numbers greater equal 1 is such a claim that can be proven by mathematical induction. Now, not all claims over natural numbers can be proven by mathematical induction. Typically, the proof technique is helpful if some parts of the statement involves a recurrence relation or some sort of recursive relationship. I try to give you an idea of how and why the technique works using a constructed example. Let's say there's a family that introduced the tradition to name its firstborn son always Caio. To differentiate the different generations of Caios, the very first son that was named Caio is Caio the first. Then his firstborn son is Caio the second. The first son of Caio the second is Caio the third, and so on. So this knowledge is given. There's nothing to prove about the naming convention. But now we want to prove that all firstborn males in the Caio family are samurais. I'm going to reformulate the claim so that it is a statement over all natural numbers. First of all, let's use the positional numeral system to represent the names of the Caios in that family. Then we can rewrite the statement that all Caios are samurais as, for all I greater equal 1, Caio the Ice is a samurai. Of course, so far we don't have any knowledge to prove the statement. So let's assume, in addition to the naming convention, we know the following. We know Caio the first is a samurai, and if a man is a samurai, then his firstborn son is a samurai as well. Then we can conclude that all firstborn males in the Caio family are samurais. Why can we do so? Well, we know explicitly that Caio the first is a samurai. But then his firstborn son, Caio the second, must be a samurai as well, because the firstborn son of a samurai is a samurai himself. Since Caio the second is a samurai, then we can also conclude that Caio the third is one, and so on. In terms of mathematical induction, the proof technique tells us that the claim Caio the Ice is a samurai for all I greater equal 1 is indeed true if we can verify the following two statements. The two parts we have to verify are, first of all, to show that the claim holds for the first natural number for which the claim is made. In this case, we will need to verify that Caio the first is a samurai. Secondly, we need to show that if the claim holds for some number k, then it also holds for the next number, that is k plus 1. So in our case, we would need to show that if Caio the case is a samurai for some number k, then Caio the k plus 1 is a samurai as well. Note that we have to verify both parts. If we can only find out that Caio the first is a samurai, then that does not mean that all the other firstborn males in the Caio family are samurais. Similar, if we know that the firstborn son of a samurai is a samurai himself, but nothing else, then we cannot conclude that the firstborn males in the Caio family are samurais. So here's a general scheme of mathematical induction. Remember, you try to prove a claim that holds for all natural numbers, greater equal some number n sub 0. You first prove that the statement explicitly holds for n sub 0. That is the base case. Then you need to go through the inductive step. You assume that the statement holds for some value k. Then you show that the statement also holds for k plus 1. The nice thing here is that when proving the statement for k plus 1, you can use the assumption that it holds for k. That is what makes the proof much easier than if you try to prove directly that your claim holds for each value k. There's a little variation called strong mathematical induction that makes life even easier in some cases. It is basically the same as mathematical induction, but in the inductive step, you not only assume that the statement holds for some value k, but you even assume it holds for all values up to some value k. So when you try to prove the statement for k plus 1, not only can you use the assumption that the statement holds for k, but also for all preceding values of k plus 1. Often it is not necessary to make the stronger assumption in the inductive step. If you're not sure whether you should use mathematical induction or strong mathematical induction, you can always start out with strong mathematical induction and make the stronger assumption in the inductive step. It is never going to harm, but often it is not necessary. It's time to see an actual proof by mathematical induction. Remember the recurrence relation for the execution time function of the recursive print method. We figured out that tprint of 0 is 1, and that for arguments greater than 0, tprint of n is equal to 3 plus tprint of n minus 1. That's how we define tprint, so that is given information. We do not have to verify anything about this definition of tprint. But then we tried to resolve tprint, and it looked as if tprint of n is equal to 3n plus 1 for all n greater equal 0. Now that is just an educated guess, and we need to prove that this is really the non-recursive form of tprint. So we have to prove that, for example, tprint of 15 is equal to 3 times 15 plus 1, and that, for example, tprint of 100 is equal to 3 times 100 plus 1, and so on. Obviously, we cannot prove the claim for each individual number separately, as there's an infinite number of natural numbers for which the claim is made. We will apply mathematical induction instead. In the base step of mathematical induction, we prove the claim for the smallest natural number for which the claim is stated. So we have to show that tprint of 0 is equal to 3 times 0 plus 1, which is 1. So let's use the definition of tprint to calculate the value of tprint of 0. Well, by definition, tprint of 0 is set to 1, which is 3 times 0 plus 1. So the claim holds for 0. Now we can move on to the inductive step. For the inductive step, we assume that the claim holds for some value k. Note that we cannot pick a specific value for k. K could be any value for which the claim has been made, so k can be any value greater equal 0. I like to explicitly write down our assumption as a so-called induction hypothesis. Then, in the actual inductive step, we can refer to the induction hypothesis if necessary. So the induction hypothesis says that the claim that tprint of k is equal to 3 times k plus 1 holds for some value k greater equal 0. Finally, we do the inductive step. And that is typically the most difficult part, so we have to show that the claim holds for k plus 1. That means that tprint of k plus 1 is equal to 3 times k plus 1 plus 1. If you have to prove an equation, you can start out with one side of the equation and then try to transform it until you get to the other side of the equation. So let's start out with tprint of k plus 1. In the end, we want to transform that to 3 times k plus 1 plus 1. In order to transform tprint of k plus 1, we can use the definition of tprint, and we can use the induction hypothesis. I first applied the definition of tprint. The recurrence relation of the definition tells us that tprint of k plus 1 is equal to 3 plus tprint of k. Note that we can only use the recurrence relation if the argument k plus 1 is really greater than 0. Since k is greater than or equal to 0, k plus 1 must be greater than 0. So we can apply the recurrence relation here. Next, we can apply the induction hypothesis. Since we know that t print of k is equal to 3 times k plus 1, according to the induction hypothesis, we replace t print of k by 3k plus 1. Finally, we transform the expression 3 plus 3k plus 1 to 3 times k plus 1 plus 1, which is the wanted expression. That concludes the proof. There are some pitfalls you should avoid. If you have a claim over all natural numbers, it is not sufficient to verify the claim for the first couple values. There's this joke about proving that all odd numbers greater 1 are prime numbers. Here's a proof by the mathematician. 3 is prime, 5 is prime, 7 is prime, while by mathematical induction all numbers greater 1 are prime. So again, it's not sufficient just to plug in the first couple values and verify the claim. The other pitfall is that you might forget the base case. Let's say we think that t print of n is equal to 3n plus 5. But we know that this is false. We know that t print of n is equal to 3n plus 1. So we try to prove in the inductive step that t print of k plus 1 is equal to 3 times k plus 1 plus 5. We basically do the same steps as in the correct proof, only the induction hypothesis differs now, as we would assume that t print of k is equal to 3 times k plus 5. Then we can indeed show that t print of k plus 1 is equal to 3 times k plus 1 plus 5. But we have only verified the inductive step. If we try to verify the base case, we will fail to do so. So make sure you always have both the base case as well as inductive step in a proof by mathematical induction.